All right, so if you're having to watch this from home today because you're absent, we're going to look at series and parallel circuits. And let's see, there's a small little lab that I'm going to have you work on after I go through today with you. So if you're having to watch this from home, you should find access to that lab on your Chromebook. All right, let's take a look at these things here. Find this spot in your note packet, please. So today, yesterday I had you guys actually try this by passing the tennis balls around. Very similar to what we see up here. There's a single pathway for current. If one device fails, everything else shuts down. Some of you may have noticed yesterday that when someone dropped the ball, literally and figuratively, we had to sort of wait till that ball got picked up so that we could then continue to pass things on. So if something fails, everything else shuts down. I would imagine some of you are familiar with a series kind of circuit that's a common household item, especially around the holiday season. Turn and tell that person that you're sitting next to where you think you might have seen a series circuit before. Hint, holiday seasons are very common for this. The Christmas tree lights, something along those lines. If you lose one light bulb because a light bulb burns out on one of those strands, the entire thing shuts down. It's a very common series circuit. Total resistance is the sum of the individual resistances. So if I had multiple resistors connected together, the total resistance would be the sum. And I want to emphasize that that goes right back to this concept, that resistance is proportional to length. The symbol that we use is an alpha sign. If I have more than one light bulb in series, effectively what that's doing is it is increasing the length of the path that the charge must flow through. So the charge is flowing through there, then it flows through there, then it flows through there. So effectively what I've done is I've increased the length of that conductive or that restrictive path. That increases the resistance. Current is equal to the voltage source divided by the total resistance. So in the event that I wanted to find the current being delivered, I would use I is V over R. The difference between this I and the other I is that this is the voltage from the battery, which is the entire voltage, and this would be the resistance of all of the devices connected together. So you might notice I is again V over R. In this case, it would be the battery's voltage divided by the total resistance. Total voltage is divided across the individual devices. What that means is that the sum of all the voltage drops is equal to the supply. Who was my battery yesterday? Okay, so Jack. Jack provided the voltage for the circuit, and you might remember that the 3 light bulbs had to take that voltage and break it into like 3 little portions. And so the idea there is that the voltage is divided amongst the individual components. The sum of all those voltage drops would be equal to the supply. Voltage drop across each device is in proportion to its resistance. Now, yesterday, I had all 3 of you bright light bulbs. Assume that you were the same resistance. Means you all glowed the same level of brightness. If you were different resistances, the one that had the bigger R value would have gotten the brighter light. So that means that there would have been a difference in how far each of those light bulbs sort of dropped that voltage. So if they were different resistances, you would see the voltage would be in proportion to that resistance. And I want to take a look at this diagram over here. Sometimes you would see a series circuit with a 12-volt car battery, and maybe it'd be in series with a 4-ohm kind of device, and then in series with a 2-ohm kind of device. Well, if the current through that circuit, and let's do some quick calculation here, I would be equal to V over R. That would be V of the battery divided by the total resistance. V of the battery is 12 volts, and the resistance, the combined, is 6 ohms, so that would give me a current of 2 amperes. We would see that this particular device, if I take V is equal to I times R, the current flowing through the 4-ohm resistor is 2 amps, and the resistance is 4 ohms. Let's try that with a smaller pen. 2 times 4 is 8. We would see that 8 volts would be dropped across that first resistor, and then the other one would get 4 volts. And so they would have a different voltage drop depending on how much the resistance is. Okay, so again, if we had different resistance values, you would see the voltage drop would be in proportion to the resistance. Okay, series circuits. We did that yesterday with passing the tennis balls around. The other kind of circuit is a parallel circuit. Parallel voltage across each device is the same. So now if you look at the arrangement of those light bulbs, you see that each has their own dedicated path. Down here, you notice that there's a lot more wiring needed. So if you're going to do a parallel arrangement, you need to have 3 independent paths for those light bulbs. A lot more wire is needed. The total current from the source is divided amongst the various branches. The idea behind that is that instead of dividing the voltage up, we're going to divide the current up. I'd like to put some numerical examples in here for you. If we have a battery that's supplying current to 3 light bulbs, one of those light bulbs is currently off because of that switch. If this current is 2 amperes and the incoming current is 5 amperes, so we have 5 amperes of current flowing from the battery. At this junction right there, we see that the current's got to split up. So if 2 goes that way, I bet you can figure out how much must be in this other branch. If the total coming in is 5, then the total going out must be 5. This one would have to be 3 amperes. And so we see that the current is sort of divided amongst those things. Okay? And so whatever comes into that node must go out of that node. The total current in the circuit equals the sum of the currents in each branch. And the big value of parallel circuits is that if one device fails, everything else can still work because they all have their own independent paths. Okay. I'm going to ask you to take a moment and consider where you have seen a parallel kind of circuit before. I'll give you a hint. It's common in your home. Turn and tell that person that you're sitting next to where you may have seen a parallel circuit before. You can't see this because I have the camera off of the people, but I'm going to ask people to raise their hand. You have experienced a parallel circuit before somewhere. Raise your hand. You've seen it. There's one. That's well, we have at least one. All right, Kylie, go. Where have you seen one? Any place in your home would be a parallel arrangement because your homes are wired in parallel. So all of your circuits that feed your bedroom, your bathroom, your kitchen, your family room, every one of those things, the home is wired in parallel. And how do you know that, Kylie? Yeah. If one light burned out and everything else shut down, that would be a series kind of arrangement like the Christmas tree lights. So these are wired in parallel. Now, the challenge with this is that as more and more devices are connected, there is more current flowing through the line wires. And I want to take a moment and talk about the safety hazard of plugging in too many components into individual outlets. So some of you have maybe seen these outlet extenders where you can take like a block of 6 outlets and plug it into one of these duplex receptacles, duplex meaning 2 receptacles. You can do that, and you can plug in 6 different things on that one outlet. The challenge is that as I plug in more things, the amount of current that is being delivered from the line wires continues to grow. You might notice that this is a 20 amp current flowing from the power supply that's from your lighting panel, the thing that's down in your basement that has those little breakers in it that if you've ever blown a breaker or tripped a breaker, you had to go down and reset. I have 20 amps there. 2 of it goes through the lamp, 2 of it goes through the heater, or 10 of it goes through the heater, 8 of it goes through the toaster. If you go in and you say, oh, I'm going to turn on a light, and that light pulls 2 amperes, so this might just be a light, that current would then go from 20 to 22 amps. And if you have a 20 amp breaker there, that's going to probably trip that breaker. Okay, so if you plug in more and more things, we have excessive current that could result in a fire. Raise your hand if you've ever used an extension cord powering some external portable device, and after you're done with that extension cord, you go to unwrap disconnect the extension cord and you're like, boy, that wire feels warm. Yeah, that's because the heat that's dissipated as the electrons sort of collide with the parent nuclei gives off this heat. If I have excessive current flowing through a wire that's designed for 20 amps and I have 25 amperes flowing through it, it's going to get a lot hotter than it should get, and that could result in fire. There are safety fuses. These are wires that melt. If you've ever done any work on an automobile, the trailer hitch wirings are not, the trailer hitch lights are not coming on. It's probably a blown fuse, because inside of your car there's a fuse box, and that fuse box has lots of different circuits, and that would just be a little wire that melts. Down near your furnace, in the event that you have an older furnace, sometimes you'll see fuses that look like this. They screw into a little box down by your furnace. If that furnace trips that or blows that fuse, you're going to end up having to replace that because they're not resettable. Now, it is a series connection, so the current flows through the filament and then to that circuit. They're replaced in most places by circuit breakers. These are automatic switches that turn off when the current is excessive. And again, you probably have done this at some point where that circuit is down. You have to go down and find that circuit breaker that has tripped and then reset it. Okay. All right, so again, some safety devices there. Your homes are wired in parallel. Now, I'm going to have you, again, I'm going to stop here in a moment. I want you to be able to build circuits. I want a big part of this class is to have you actually build circuits with actual wiring and batteries and lights and stuff like that, but I cannot have you do that until I know that you can construct circuits virtually. Yesterday I had you guys do an introduction to circuits so you could figure out how to use these wires and connect things up. Today what I'm going to have you do is I'm going to have you do another virtual lab in the event that we have everyone getting these things done. And I feel comfortable in a class with 28 kids. I feel comfortable that we can actually build circuits safely, then we will build some circuits on these tables. If, however, people are not getting these things done, I do not feel that people can work safely, we will not build circuits in this class. There is too much potential for people to get injured or equipment to be damaged. So if you want to actually build circuits and you want to actually get wiring out to do that, I need you to complete these labs. You need to pay attention to what we're talking about and use these meters, because we will not just go and have a free-for-all and you just build circuits. You have to know what you're doing. So on these simulations, these things that I'm giving you, pay attention to what you're doing. Work safely. Well, here you can make a fire and it's not going to actually cause damage to anything. Raise your hand if you had it connected yesterday and you saw fire going around. Yeah, we do not want that to happen when you're actually building circuits. So only if I feel comfortable that we can do it would we do this. So please be extra careful when you're doing these things. All right, here's the, I'm going to stop the video. If you're watching this from home because you're absent today, the link is on your classroom page, and then you would go through and do that.